An isotope has a different number of neutrons, and this different number of neutrons is going to affect the mass. So the mass is that. And we can see this when we write the isotope. The mass is going to be how we name the isotope. So the number that comes after the name is going to be the mass of that particular isotope. We can also see that it's the same number that goes at the top left. So again, the mass is what gets changed because of those different number of neutrons. And the mass, some of us wrote the number to the right of the symbol. The mass and the atomic number always go to the left of the symbol, okay? So that's our mass. And then the atomic number is what goes at the bottom left. So the atomic number goes to the bottom left. This is also the number of protons. And we can find that number on the periodic table. And so we can tell that this is the same element because the bottom number is the same. So if I had an isotope that I didn't know what it was, and I symbolized it as X, and I had a mass of 52 on one of them and 55 on the other one, but the bottom number was the same, like this, I would know that those are isotopes of the same element because the bottom number is the same. And I know they're isotopes because the top number is different. So these two guys here, these are isotopes of the same element, and I know that because of that bottom number. So when we name an isotope, we name the element, and then we name the mass. So if I'm just given a name and a mass, I may have to look on my periodic table to find out the atomic number. If I'm given isotopic notation, then to find the atomic number, I can just look at the bottom left number. So both of these carbon atoms have 6 protons in them. And all of our atoms so far have been neutral. So that means that our protons are equal to our electrons. Got 6 electrons to make it neutral. Now the last thing that I have to do is I have to figure out how many neutrons I have. Neutrons, the mass is equal to our protons and our neutrons. Well, we know our number of protons because we've got our atomic number. So that means we can take our mass and subtract our protons to find out our number of neutrons. So I can go ahead and I can take my mass of 12 for carbon 12, subtract my protons, and that means that I have 6 neutrons in carbon 12. In carbon 14, I have my mass of 14, and I can subtract, again, still 6 protons because it's still carbon, and I would have 8 neutrons. So we can see then that our difference between these isotopes is the number of neutrons, and we can see that that affects the mass. So the first thing I have here is a definition of alpha decay. Alpha decay is when we have the decay of a parent isotope, so notice I'm using vocabulary, releasing an alpha particle. And then I say what an alpha particle is. An alpha particle is made up of 2 protons and 2 neutrons. So that tells me a couple of things. When I write my alpha particle, down here as one of my pieces of a result of this alpha decay, I need to make sure that it has those components, 2 protons and 2 neutrons. I also have my parent isotope, which is the material that is decaying. I have it written in proper isotopic notation with the mass of 210 being my top number. And then I look on my periodic table to find that the number of protons, my bottom number, is 82. When I write a nuclear decay equation, I always start with my parent isotope, and then I draw an arrow to show that it is going through the decay. And so this is a process of fission. This means that we have one nucleus breaking apart into more than one piece. And we can see that with the alpha particle and then our plus sign and our daughter isotope. So we've got 2 pieces at the end. So I've got this big nucleus that has 82 protons in it and a whole bunch of neutrons. I could figure out my neutrons by taking 210 minus 82. And an alpha particle is going to shoot out of that nucleus. The alpha particle is made up of 2 protons and 2 neutrons. So I'm going to put a 2 on the bottom for my 2 protons. Now remember, the top number is our mass, and protons and neutrons both contribute to mass. So 2 protons and 2 neutrons means that this nucleus has a mass of 4. So now I look on my periodic table, and the element that is 2 protons is helium. So that means that essentially an alpha particle is a nucleus of helium. Now, my daughter isotope is the big nucleus that's left over. Since the nucleus lost 2 protons, 2 of the protons are now in that alpha particle, I now only have 80 protons in my daughter isotope. And because a total mass of 4 was in that alpha particle, my new daughter isotope only has 4 less mass to it. So it only has a mass of 206. So now I look on my handy dandy periodic table, and I find that number 80 is mercury, capital H, lowercase g. Decay, I have a neutron that is in the nucleus of that starting parent isotope. So essentially, here's my neutron. What it's doing is it's decomposing, which means it's breaking down into 2 different pieces. It's breaking down into a proton and an electron. So the electron is my beta particle. This is the piece that is being emitted. So we've got a starting parent isotope of potassium right here. And that parent isotope has a mass of 40. I'm going to first put my beta particle, which is my electron. That is being emitted out of the nucleus. So we write an E for electron. Electrons from last unit we learned don't have much of a mass. So we put 0 on the top because no mass is being lost when that electron shoots off. Now an electron, normally that bottom left number is a number of protons. Obviously an electron is not a proton. So what number do we put on the bottom? We're going to put the charge of the electron on the bottom. So we put a -1. This is also going to help us with making sure that we've got the right daughter isotope. So isotope still has a mass of 40. Now, remember, we have a neutron from that big potassium turning into a proton. So if our potassium nucleus had 19 protons, and one of the neutrons turns into a proton, now we have 20 protons in our daughter isotope. We look on our periodic table. Number 20 is calcium. Capital C, lowercase a. And so I can check my work. I can check and see 20 plus a -1 should equal the 19. And it does. That I'm going to start with when I explain half-life is I'm going to give a definition. So half-life is an amount of time. So if I ask you for a half-life, the units should be always something that has to do with time. Minutes, seconds, hours, days, years. Your unit should always be a unit of time. So half-life is how long it takes for half of a radioactive isotope to decay into a more stable isotope. So let me give you an example. Let's say I have 500 grams of a radioactive isotope, and it is unstable. I give you the graph right next to it and say, what is the half-life of this material? So I need to find out how long does it take for me to go from having 100% of my material to having only 50% of my material. So if I look at this graph, it shows starting with 100% of my unstable material. So my 500 grams would be my 100% for this example. How long does it take for me to have only 50%? Now, if I had a graph of grams, I would be looking for 250 grams. But I don't. This graph has it in percentages. So I'm looking for at what time do I have 50% left. So I'm going to look, and at 50% left, that took 4 minutes. So it took me 4 minutes to go from 100% down to 50%. And I can check and see, okay, what if the next half-life happens? What if I go down to 25%? So now I'm going to look at my graph again. I'm going to go across until I hit 25% and down. And I look, and yeah, that took another 4 minutes. Now it had to take a total of 8 minutes for 2 half-lives to happen. So this took another 4 minutes, or a total of 8 minutes for 2 half-lives. If I look at my third half-life, which would be another half of the material, which would be breaking it down to 12.5%, I can see that took another 4 minutes, or a total of 12 minutes for 3 half-lives to occur. And so I can also look at this in terms of 1/2 to a power. 1/2 to the first power is going to be 50%, or 1 half-life. 1/2 to the second power is going to be 0.25, or 2 half-lives. And a third half-life is going to be 1/2 to the third power, or 0.125. This is my third half-life. So we can see there's a relationship. 1/2 to the third power is 12.5%, or 0.125. To the fourth power, to the fifth power, to the sixth power, I could calculate all of those. The next question says, how much of a 250 gram material would be left? So left is my unknown. My 250 grams, that's the amount I'm starting with. And it says after 32 minutes. Equation that we learned is the amount left is equal to the amount we start with times 1/2 to the number of half-lives. And we also learned that if we don't know our number of half-lives, we can calculate our number of half-lives by taking the time that has elapsed and dividing it by the time of 1/2 life. Let's figure out our n first. The amount of time that has elapsed is 32 minutes. And the amount of time that is a half-life is 4 minutes. 8 half-lives have occurred. The amount that I have left is equal to the amount I start with, which is 250 grams, times 1/2 to the 8th power, because we've gone through 8 half-lives. So the first thing I'm going to do on my calculator is I'm going to do 1/2 to the 8th power, 0.0039. If I wanted to know what percentage is left after 8 half-lives, I could multiply that number by 100 to put it in a percentage. So in a percentage, this would be 0.39% is left. So if I have the question, what percentage is left after 8 half-lives, take 1/2 to the 8th power and then convert it to a percentage. Multiply by 100. So now that I know that, I can do 250 times 0.0039, because that's 1/2 to the 8th power, is 0.98 grams. And there's my final answer. So our next problem says, if you are left, so this is the amount I'm ending with, after 12 half-lives, so here's our n, what was the original amount? So how much did we start with? So same equation. The amount left is equal to the amount we start with times 1/2 to the number of half-lives. So this time, I know how much is left. And I'm going to set that equal to my original amount, which I don't know, that's my unknown, times 1/2 to the 12th power. So I want to solve for x in this problem. The first thing I'm going to do is I'm going to find out what 1/2 to the 12th power is. So I'm going to put that in. That is simply 2.44 times 10 to the negative 4th power. These three numbers here are all the same. Just think algebra. What do?
Divide.
I'm going to divide both sides by this number right here. 2.44 times 10 to the negative 4th. Or this number. They're the same number. So I'm going to divide both sides, 132.8 grams. So this is what I started with.